Hello everyone, my name is Meenakshi. Today's topic is IR spectroscopy. What are the principles of infrared spectroscopy? The atom in a molecule are in a state of constant vibratory and rotatory motion. The different ways in which the vibration can take place are as follows. For diatomic molecules, let us say we have a molecule XY. It can stretch the XY bond inward or outwards in the following ways. The compression and extension of the bonds take place along the XY bond. For triatomic molecules, let there be a molecule XYZ with a bond angle XYZ. Here we have two types of a moment stretching. As in the case of XY diatomic molecules, there will be stretching in the XYZ molecule too. There two bonds are involved, XY and YZ bonds. Let us assume that the molecule in linear. The different stretching force that are manifested are as follows. Bending. If the molecules in is angular, there will still be stretching of XY and YZ bond. Besides, there will be some bending force between XY and YZ bonds, as a result of which the angle XYZ will change. It will increase and decrease continuously as shown below. Those there are a number of vibration and rotation changes taking place in the molecule. On observation of light, the molecule are excited from lower vibration and rotational level to higher ones. For affecting such transition, frequencies in the infrared range are good enough. Molecule will absorb such frequencies as are needed to excite molecules from lower vibrational level to permitted higher levels. Absorption of energy by a bond increases the amplitude of a vibration. Every bond and every functional group has a specific absorption frequency which is calculated to excite the molecule to higher vibrational or rotational level. A graph between the amount of absorption of infrared lights against the frequency of this light is called infrared spectrum. The following diagram illustrates various frequencies in the higher range associated with various bonds in alcohol molecules. What is the range of infrared radiation? What are the units used in infrared spectroscopy? IR region has the range of 0.2 to 20 μm or 800 to 20,000 nanometer. The region between 0.8 to 2.5 μm is called the near infrared region, and the one between 15 to 20 micrometer is called for far infrared region. The region between 2.5 to 15 micrometer is the proper infrared region. Generally, wave number, which is the number of vibration of the radiation per centimeter, is used for describing IR spectrum. The unit of wave number is centimeter inverse. The other unit which is used in connection with IR spectra is micrometer. The relation between micrometer and centimeter inverse can be established as given below. 1 micrometer is equal to 10 raised to power minus 6 meter is equal 10 raised to power minus 4 centimeter. If is given in micrometer, it has to be converted into can be multiplying by 10 raised to power minus 4. Those wave number is equal to 1 by lambda into 10 raised to power minus 4. W wave number is equal to 10 raised to power 4 by omega centimeter inverse. Give the IR absorption bond of some important bond and functional group. The table below gives the bond type of compound, the absorption wavelength and frequency and intensity of absorption. In the column of intensity S, M, W and V stand for strong, medium, weak and variable respectively. Some characteristic infrared absorption frequencies. Alkene wavelength in micrometer 3.28 to 3.51. Frequency in centimeter inverse 2850 से 2960. इंटेंसिटी ms m2s. Alkenes wavelength 3.22 to 3.32. Frequency 310 to 3100 m. Alkynes 3.03 wavelength and frequency is 3300. Intensity S. Aromatic rings 3.22 to 3.33 wavelength and frequency 3000 to 3100 m. Aldehydes 3.47 to 3.77 wavelength and frequency 2060, 650, 200, 2880 W. Often 2 bonds. Alkenes wavelength 6.66 to 16.66. Frequency 600 to 1500 W. Alkenes 5.95 to 6.2. Frequency and wavelength 1620 1 to 1680 V. Alkynes frequency wavelength 4.42 to 4.76 to frequency 1500 to 1600. Nitro compounds वेवलेंथ है 6.5 to 7.5 and frequency is 1330 to 1540. Write note on functional group region, fingerprint region. Functional group region, the region of 2.5 to 7.4 micrometer, frequency 4000 to 1430 centimeter inverse, is related with vibrational change in the functional group in the molecule. By observing absorption in this range, we can draw some conclusion regarding the functional group present in the molecule. Hence, the region is called the functional group region. Fingerprint region. It is found that the region 7 to 11 micrometer given a good deal of information regarding structure of the compound and various other groups beside the functional group in the molecule and their relative position. The region is called the fingerprint region. Frequency in the fingerprint region can lead, lead us to identify a given compound. How does the absorption frequency of a group change from compound to compound? In the table of higher absorption frequency, it is the range and not a particular frequency which is given. This is because the absorption frequency depends not only upon the group but also upon the environments of that group. Example, the other bonds and groups which are associated with that particular group in the molecule. We find that there is a slight variation in the absorption frequency if the environment are changed. This is illustrated in the table below, which give the absorption frequency due to the carbonyl group in different compounds. Acetone CS3C double bond OCS3, frequency 1700 centimeter inverse. Compound cyclobutanone, frequency 1780 centimeter inverse. Methyl ethyl ketone CS3C double bond O CS2 CS3, one frequency 1710 centimeter inverse. Methyl vinyl ketone CS3C double bond OCH double bond CS2, one frequency is 1680 centimeter inverse. Cyclohexane known, one frequency 1710 centimeter inverse. Cyclopentanone, frequency is 1750 centimeter inverse. Important. Negative evidence is very reliable in interpreted the higher spectrum of a compound. If an absorption frequency corresponding to a particular group is missing from the spectrum, it is almost sure that the group is absent in the molecule. How do you record the higher spectrum of a compound? Answer. IR spectrometer consists of the following components: IR radiation source, inner nest glower, which is a rod made of an alloy of zirconium, deuterium, and erbium oxide, is used as IR radiation source. It is electricity heated to 1750 Kelvin. Rock salt cell and prism. Glass and quartz absorb IR radiation, hence this material cannot be used for making cell for the sample and for prism, which are used in the optics of the IR spectrometers. Rock salt or some similar material is used for this purpose. Sample preparation. Generally, the sample in the form of solid is avoided because it scatters the radiation too much. For obtaining better spectra, the sample is taken in the form of potassium bromide disc, a mixture of the sample and KBr. Second technique is to grind the sample with Nuzol, which is a highly purified form of petroleum to obtain Nuzol mole, which is objected to investigation. Third technique is to dissolve the sample in pure CHCl3 or CCl4. Solvent like water and alcohol are avoided in special case. The substance is gaseous may be taken as such. Recording of spectra. The sample to be investigated is placed in the path of IR rays. The intensity of transmitted light is measured automatically, and a graph between the intensity of a transmitted light and the wavelength is obtained. How is the frequency of vibration of a diatomic molecules related to reduced mass? What is Hooke's law? The vibration of diatomic molecules may be compared to those of a simple harmonic oscillator, in which the force tending to restore an atom to its original position is proportional to the displacement of the atom from the position. This is called Hooke's law. In other words, a covalent bond may be considered as a wavelength, wave weightless spring. The restoring force F acting upon it when it is stretching to distance x is given by Hooke's law. F is equal to minus kx, where k is the force constant of the spring or bond. A molecule may therefore be considered as a collection of balls and springs, where the balls are atoms and the springs are the chemical bonds. As a direct consequence, a vibrating diatomic molecule can function as a simple harmonic oscillator. The frequency of its vibration V is given by V is equal to 1 by 2 pi c under root k by r, where r is termed the reduced mass of the diatomic system. It is calculated from the expression r is equal to m1 m2 l bracket m1 plus m2 bracket of, where m1 and m2 and are the masses of the two balls. C is the velocity of light. Such a simple mechanical analogy explains the position of various absorption in the infrared spectrum from the nature of the atoms and the strength of the bonds between them, as illustrated below. 1. The smaller the constituent atom of a diatomic molecule or group, smaller is the reduced mass R and therefore higher its vibrational frequency. The bond between hydrogen and other atom have the highest now fundamental frequencies, but covalent compound of halogens of most metals show infrared absorption of very low frequency, which are too low to be recorded on a routine spectrometer. The force constant K is a measure of the strength of the bond and therefore it increases with the increase in bond order. As such, vibrational frequency also increases with the increase in bond strength or bond order. For example, the stretching frequency increases as we move from CC C bond C to C triple double bond C to C triple bond C. What is the number of fundamental vibration in case of diatomic and polyatomic molecules? The number of fundamental absorption bond exhibited by a molecule is related to the fundamental ways of vibrating or vibrational mode available to a molecule. In general, number of fundamental absorption bond equal to number of fundamental vibration modes. Since a diatomic molecule has only one fundamental vibration mode, it gives rise to one fundamental absorption bond band. However, polyatomic molecule can have more than one kind of vibrational movement. They exhibit more than one fundamental absorption bond as given below. Nonlinear polyatomic molecules. It has been found that a non-linear polyatomic molecules can have 3n-6 modes of fundamental vibrational where n is the number of atoms present in the molecule. For example, water n is equal to 3 has 3 vibrational modes, each of, each of which can give a absorption band. Linear polyatomic molecules. Linear polyatomic molecules having n atoms can have 3n-5 fundamental vibrational. For example, carbon dioxide n is equal to 3 has 4 vibrational modes. Example 3 into 3 minus 5. In case of larger molecules, the number of fundamental vibration increase very rapidly with the increase in the value of n, but it has been observed that the number of fundamental bands actually obtained is usually less than that expected from the theoretical number of fundamental vibrational. This may be due to the following reason. Some of the fundamental vibrational may be very weak and therefore may not be recorded as bands. Some of the fundamental vibrational may be very close and as a result overlapping of band may take place. What is selection rule? Selection rule. Most of molecule possess dipole moment due to unique sharing of electron within the bonds linking the constituent atoms. When a polar bond undergoes stretching vibration along the internuclear axis, the electron distribution changes. As a result, dipole moment also undergoes a change. In other words, a vibrational produces a fluctuating dipole moments. Interaction between the oscillating dipole moment and the infrared radiation led to the absorption of energy from the radiation. The interaction can occur only if the dipole moment at one extreme of the vibration is different from the dipole moment at the other extreme of the vibration in a molecule. There are certain rules now a selection rule which determine whether a vibration would be effective for a particular type of spectrum or not. For infrared spectrum, the rule is that only those vibrational are effective in causing absorption which are not central Symmetric. Example, the vibration are not symmetrical but the center of the molecules. Since most of the functional groups on organic chemistry are not centrosymmetric, they respond very well to infrared spectroscopy. Given the application of infrared spectroscopy, answer some of the important application of IR spectroscopy are given below. Identify of the functional group. Every functional group absorbs IR radiation in a particular range, irrespective of the compound is which such group is presented for. Example, a carbonyl group gives IR absorption bonds in the range of 1650 to 1750 centimeter inverse. Hence, by observing the absorption frequency, we can tell something about the functional group in the compound. Determination of structure. Investigation of the IR spectra in the range 2.5 to 7 micrometer gives us information regarding functional group present in the molecules. Further, the IR spectra in the fingerprints region give us an insight into various other groups and their relative position. The two studies together help us to arrive at the extra compounds, testing purity of a compound. Generally, a pure compound has defined and sharp absorption frequency, whereas as the spectra of an impure compound has diffused and blurred lines due to additional impurity materials present in the sample. Higher spectra of may pure compound are available in literate literature. We can compare the higher spectra of the unknown sample with that of the pure sample. If to tell exactly the sample is pure, otherwise not. Following program of a reaction. During the course of a reaction, many intermediate compounds are formed which change into the product. This infrared intermediate compound can be identified by IR spectroscopy. IR spectrometer records the spectra continuously, and by interpreting them, we can follow the reaction. The mechanism of the reaction can be proposed. Thank you.